Here we are with question number 5 on homework 10. 2x squared y double prime plus xy prime minus y equals x, with one solution to the homogeneous version of this being x and x being greater than 0. So the first step is to say y2, the second component of the homogeneous version of this, is a function u times x, and y prime is the following, y double prime is the following. You'll see why we went to the trouble of writing that out, because in this step we will operate this differential equation on y2 and set it equal to 0, because again y2 is a part of the homogeneous version of this equation. It is a solution to the homogeneous version. So when we plug this in, this is what we get. And simplifying, gathering terms, we get u prime prime plus u prime times 5 over 2 times x to the negative 1 equals 0. Here we do the reduction of orders step. That is, we say some function u equals u prime, or w equals u prime, and w prime equals u prime prime. Making that substitution, it becomes a first order differential equation that we can solve using the integrating factor method. So these are the steps for doing that. P of x is 5 halves x to the negative 1, so the integrating factor is x to the 5 halves. The W1 isn't terribly important, I don't think, unless I used W again later on in my notation. In any case, well, it would be important if I didn't write W1 here. There we go. Now we're consistent. Using the integrating factor method, we arrive at the conclusion that W equals some arbitrary constant C1 times x to the negative 5 halves. Then we integrate this, and that gives us u, since W is u prime. So u is the integral of C1 times such and such, which is some new arbitrary constant because we modified it by dividing. We modified C1 by dividing by negative 5 halves. So this is the integral, and to be honest, you'll see why soon, but we're not particularly concerned with adding a constant of integration here on the right. That will be clear in a moment. So since u is this, y2 is u times x, as we set up here. So u times x is x times x to the negative 3 halves, which is x to the negative 1 half. Now y2, as we said, it was a part of the complementary solution to the differential equation, that is the homogeneous version of it. So we know that the linear combination of x to the negative 1 half and x is going to give us the entirety of our all linear combinations of those two things is going to give us the entirety of our solution space to the complementary solution. What that means is, since I labeled C1 and C2 up here, I just went ahead and said, okay, this is x times C3, some arbitrary constant, plus C4 times x to the negative 1 half, some other arbitrary constant. Now to find yp, since x is in the fundamental set of solutions for the homogeneous version, and the differential equation is equal to x up here at the top, there's a relationship between the two, so yp is some function v times x, etc., etc. So we'll now operate the differential equation on yp and set it equal to x, since this should give us the solution to the non-homogeneous version, the particular solution, that is. So expanding, or substituting and then collecting like terms, we get this, and simplifying it into a more standard form, a more general form, where this has no non-constant coefficient. It's pretty easy to see that this can be solved using another reduction of order and integrating factor. So after saying z equals v prime, z prime equals v prime prime, we've reduced the order down to first order. Here's our integrating factor. Here's our solution steps. Here are our solution steps. And we find that z equals 2/3 times 1/2 times x to the 3/2 times x to the negative 5/2, which simplifies to 1/3 x to the negative 1. And since z is v prime, we integrate z in order to find v. That gives us integral of 1/3 x dx, which is 1/3 log x. And since yp equals v times x, we get yp is x over 3 times log x. And our solution in its entirety is yp plus yc as shown.